This is Lesson 7 from Unit 11, Strong Acid, Strong Base Titration Curves. So we can determine the concentration of hydronium or hydroxide ions experimentally by using titration or by measuring the pH. When we did the titrations previously, we used an indicator solution. So we had potassium hydroxide, or in our case sodium hydroxide, in the burette. And then we had acetic acid when we did the titration with phenolphthalein in the flask. And when the color turned pink, you knew that the titration was complete, that the moles of acid equaled the moles of base. What we're going to be doing now is tracking what happens in a titration by tracking the pH. We will not have an indicator present. And we're going to be looking at 4 different types. Titrating a strong acid with a strong base, titrating a strong base with a strong acid, titrating a weak acid with a strong base, and titrating a weak base with a strong acid. So we're just going to start with the first one, titrating a strong acid with a strong base. So here's the example here. We have a 50 ml sample of dilute nitric acid is titrated with 20 molar, 0.2 molar sodium hydroxide. And we're going to be tracking the pH as we titrate to determine the concentration. So this is a typical curve for titrating a strong acid with a strong base. We have a pH right here of 1. So our pH is equal to 1. That actually tells us right off the bat that our initial hydronium concentration is equal to 0.10 molar. Remember that we can just take 10 raised to the negative pH to determine the concentration. As we begin to add KOH, the pH begins to slowly increase until we reach the equivalence point at a pH of 7. And for a strong acid, strong base, this equivalence point will always be 7. This is one way to detect that you have a strong acid, strong base titration. So, what reaction is taking place as the reaction proceeds? We have the nitric acid reacting with the sodium hydroxide, and we're making water and sodium nitrate. If you remember from our analysis of salts, sodium ions do not have any impact on pH, and neither do nitrate ions. So we end up with a completely neutral solution where H plus and OH have the same concentration. There are some features of a strong acid, strong base titration curve that you should be familiar with. So let's take a look at what you should be familiar with. So the initial pH is going to be very low. The initial pH is the same as the strong acid concentration, so we know the concentration simply by looking at the pH if we know we have a strong acid. The pH increases very slowly for about the first 90% of the titration, and this is because pH is a logarithmic function. At the equivalence point, the pH is always going to be 7. This is where the moles of added hydroxide match the initial moles of hydronium ion. We can use the mLs of the equivalence point to solve for the unknown acid concentration. After the equivalence point, the pH is going to increase as the hydroxide ion becomes the excess reagent. Okay? So, solving a problem like this one, if we wanted to solve for the concentration of the pH, or excuse me, of the hydronium ion concentration without using the initial pH, we could use a shortcut that will work only for 1-to-1 ratio problems. And I know I told you earlier, don't do this because you were too new to really recognize when you had a polyprotic or monoprotic acid. So this will only work for 1-to-1 ratios. A stands for acid, and B stands for base, and we will use this for 1-to-1 ratios because it makes life a whole lot easier. So if we look at the above problem, we did not know the concentration of our acid. the volume of our acid was equal to 50 mLs, and I'm referring way up to the top of the problem. The molarity of the base was 0.20 molar, and the volume of the base was 25 mLs. And so we just set this up as Ma times 50.0 mLs is equal to 0.20 molar times 25 mLs. And when you do that, you get Ma is equal to 0.10 molar, which we already knew just by looking at the pH.